We will now go on to look at mixtures of ideal gases. The most common mixture of them, of course, is air. So, where we have nitrogen and oxygen and other trace elements which are mixed together. We know that each of these gases, for example nitrogen, we can assume it to generally be an ideal gas in the kind of temperatures we are usually interested in. Similarly, oxygen can be usually assumed to be an ideal gas. So, the question is, what happens when I mix these two together? Does it behave like an ideal gas? Can I find out what its properties are, and so on? So, in order to do this, we can think of, for example, a system where we have mixed the gases together. We can think of the mass of each of these gases as small m. For example, m1 can represent the mass of nitrogen, m2 can represent the mass of oxygen, and so on. So, we can look at a system like this. We can also look at the number of moles of each of them. So, for example, if n1 represents the number of moles of nitrogen and n2 represents the number of moles of oxygen, for example, then what we know is that the total number of moles we can get, which is we can just call it as some n. The total number of moles would be the number of moles of N2 plus the number of moles of oxygen, which is essentially given here in this formula for a mixture of any number of gases. So, if I had some capital N number of gases, the number of moles which I have will be N1 plus N2 plus N3 plus and so on up to N sub capital N, which is essentially equal to summation over Ni, where Ni is the ith species. Similarly, if I had a mass of m1 which represents nitrogen and m2 which represents oxygen, then the total mass is m, which must be equal to the sum of the individual masses. So, these are just mixtures, and there is mass conservation. Mass can neither be created nor destroyed. So, it is here and this shows here, and we also have conservation of moles here because there is no chemical reaction of anything of that kind going on. So, we see that m, which is the total mass, must be equal to the sum of the individual masses, which is again shown by this formula, where we say m is m1 plus m2 plus so on up to the last species if we have n number of species. So, essentially that is summation of m of the ith species. We use a few other things over here. One of them is what we call as the mole fraction, which is the number of moles of any of the species divided by the total number of moles. So, for example, if I wanted the mole fraction of nitrogen, that would be N1 divided by N1 plus N2, the number of moles of nitrogen divided by the total number of moles, and N1 plus N2 is also N. So, I can write this as N1 by N. So, that would be the mole fraction of nitrogen, which I would normally denote as Nx2, or in this case, because I am using 1 to denote Xn2, or since I am using 1 to denote nitrogen, I would also call it as X1. So, that is given by this formula here. So, the mole fraction of the ith species is the number of moles of the ith species divided by the total number of moles in the mixture. So, this tells us how many moles there are of that species compared to the total number of moles. In a similar fashion, we can also define what is called as a mass fraction, which tells us what is the mass of a particular species compared to the total mass of the mixture. So, if I wanted to do the same thing for nitrogen, the mass fraction which we denote as y, so mass fraction of N2, which is also equal to y1 because we are using the subscript 1 for nitrogen and the subscript 2 for oxygen. This would be the mass of nitrogen divided by the total mass. In this case, if I just have mixture of nitrogen and oxygen, it is the mass of nitrogen plus the mass of oxygen. But more generally, I could write this as some m1 divided by m1 plus m2 if I have two species. If I had a large number of species, I would write mi, which is where I can be any number depending on what I want. If I want n2, I is 1. If I want O2, I is 2, and so on. So, mi divided by the total mass, which is m, and the total mass we saw from here is sigma of m. So, we have here mi by sigma of mj, where j is 1 to n. So, the bottom essentially says that we should sum up all the masses of the individual components, and the ratio is what we call as the mass fraction. So, this tells us what is the quantity of mass of one of the gases compared to the total mass of all the gases which we have in that volume. Since we defined the mole fraction in this way and the mass fraction in this way, if I was to take a summation of all the xi's, all the mole fractions, for example, if I had only two gases 1 and 2, if I was to take x1 plus x2, by definition x1 is essentially n1 by n1 plus n2, x2 is n2 by n1 plus n2. This is how we defined as x1, this is how we defined x2. So, if I sum up these, essentially I get n1 plus n2 by n1 plus n2, which is equal to 1. And similarly, if I had a large number of species, if I summed up the mole fractions of all the species, the sum should be 1, and we can also see the same for the mass fractions. If I was to take the summation over here, so 1 represents right now nitrogen, so that is the mass of nitrogen divided by the mass of nitrogen plus mass of oxygen, that is my y1, and y2 is mass of oxygen divided by this, which is essentially one. So, we see that if we sum up all the mole fractions of all the components in the mixture, or if we sum up the mass fractions of all the components in the mixture, the sum is 1. So, which is essentially what is given by mathematically this formula. So, it says if you sum up all the mole fractions you get 1, if you sum up all the mass fractions you again get 1. We can look at conversions of these various quantities from one into the other. So, capital M represents for us the molecular weight or molecular mass as it is called, which is essentially the mass of 1 kilomole of substance, the mass in kg of 1 kilomole of substance. So, if I have n moles of a certain substance, let us say if I had n1 moles of a certain substance and the molecular weight is m1, and the units of this would be kg per kilomole, and if I had n kilomoles of a substance, if I multiply n1 kilomoles by this would have units of kilomoles, this has units of kg per kilomole, and the kilomoles will be cancelled and I would get something which has the units of kg, which is essentially the mass. So, what I see is that if I multiply the number of moles into the molecular weight, I get the mass. Similarly, for a second species, if I multiply m2 into if I multiply n2 into capital M2, I get this and so on. So, for the nth species, we say if I multiply number of moles into the molecular weight of the nth species, I would get the mass of the nth species. And we know that the total mass is the sum of the individual masses. So, the total mass, which is m, is sum of mi, that is by definition, which is now equal to sum of these. So, it is sum of the number of moles of each species into the molecular weight of that species. So, we now have another way of finding out the total mass by if we know the number of moles of each species. Of course, if we directly knew the mass of each species, we could just sum them up directly. And since we defined the mass fraction in this way, what we can also do is now we can define the mass fraction slightly differently. So, we have this mi by m. In the place of mi, we can actually put ni into capital Mi. So, we can do that. So, the mass of the ith species, what we had over here, is essentially the number of moles of the ith species into the molecular weight of the ith species. And what I can do is I also have the other formula, which is the total mass m is the number of moles summation of the number of moles of each species into the molecular weight of the corresponding species. This is also something which I have. What I can do is divide each of these by the total number of moles. Okay, I am going to have a little trouble writing here. So, this n is actually this m divided by n, and now I can call these 1 and 2. If I divide one over the other, 1 over 2, then I get mi by m is ni by n, which is the mole fraction, and I have ni by n, which is again mole fraction. N is a constant, there is no I over here, this is a constant. So, ni by, I can take this within the sigma. So, ni by n is essentially this, and I get this. So, this is of course the mass fraction of the ith species, which we can now write in terms of this formula over here. So, earlier we wrote it in terms of individual masses. Now, we can also write it in terms of either the number of moles or in terms of the mole fractions. Both of them is something which we can do. In a similar fashion, what we can look at is the molecular weight of the mixture. So, the molecular weight of the mixture is now given by this formula over here. So, the molecular weight of the entire mixture is the mole fraction of each species into its corresponding molecular weight, sum over that, which gives us a molecular weight of the mixture. So, the molecular weight of the mixture is essentially the so we have in each of these cases the molecular weight of an individual species is the ratio of the mass of the species to the number of moles of the species. So, the molecular weight of the mixture is the ratio of the mass of the mixture to the number of moles which are there in the mixture, and that is essentially given in this fashion over here. We can also find ways of converting mass fractions to mole fractions and so on, but before that I would like to also once again remind you, if we are using the alphabet Y to denote mass fractions, and we are using X to denote mole fractions. Some books use this terminology the other way. So, if you are going to look at this in any of the textbooks, please watch out as to which is Y and which is X in the notation used in that particular book. What I can now do is find out a formula to convert the mass fractions into mole fractions. So, if I take for example 1 kg of a mixture, then if I want to find out the mass fraction of any species in that mixture, the mass fraction generally is mass of that component or mass of the species divided by the total mass. In this case, because the total mass is 1 kg, the mass of any component also represents the mass fraction of that component. In general, when I know the mass of a component, if I want to find out the number of moles, what I would do is divide the mass by the molecular weight. So, molecular weight has units of kg per kilomole. If I divide mass, which is in kg, and divide it by kg per kilomole, the kilomole goes back to the numerator and I get units of kilomole, which gives me the number of moles. So, in this fashion, what I would do normally is find N1 is mass of component 1 by molecular weight of 1, N2 is mass of component 2 by molecular weight of component 2, and so on. But in this special case, since I have taken 1 kg of mixture, instead of mass of component 1, I can write Y1, and therefore I get number of moles N1 is Y1 by molecular weight of 1, number of moles N2 is Y2 by molecular weight of 2, and so on, as we see in the first line of the slide. If I want the total number of moles in the mixture, what I would do is sum up the individual number of moles of the components, and so therefore I get N, which is sigma of Ni, that is equal to sigma of yi by molecular weight of I, as shown in the second line. I have taken 1 kg of mixture, and that 1 kg of mixture now has n, or sigma yi by mi, number of moles. So I can also find out what 1 mole of this mixture would weigh, and that would essentially be 1 by sigma of yi by mi, and that quantity is what we usually call as the molecular weight of the mixture. So what I see is the molecular weight of this mixture would be 1 by sigma of yi by mi. So finally, what I can do is I can find out the mole fraction of every species, which I would get generally as Ni by N, the number of moles of each species by the total number of moles. We see from the first line that Ni is Yi by Mi, or N1 is Y1 by M1, and so on. And the total number of moles is what is given in the second line as sigma of Yj by Mj. So putting these two together, I get a formula for converting converting mass fractions into mole fractions, as Xi is Ni by N is Yi by Mi into the molecular weight of the mixture, or Yi by Mi divided by sigma of Yj by Mj.